So we're going to do a couple more examples together. Now focusing in on not using Debye-Huckel theory, but focusing in on using tables of activity coefficients to be able to make some approximations for what the behavior of ions in solution are when we actually consider activities instead of just concentrations. So the example that we're going to start off with is we're going to use a table, right? Your table with our activity coefficients, just to be completely clear, to determine H plus and pH of a 0.100 molar HAC solution in 0.1 molar KCl. Okay. I've reminded us here that in H2O we had, with Debye-Huckel theory, all right, an H plus that was about 1.37 times 10 to the minus 4 molar, and a pH that was 2.8797, okay? So what we're going to do is we're going to see, okay, well, what are the effects of actually putting more salt in there? Again, just to review, the Gen Chem answer is nothing. This would have no effect. And now our answer is, well, the K pluses and the Cl minuses that go into solution are going to affect the ionic atmosphere. And because they're going to affect the ionic atmosphere of the H pluses and the AC minuses, it's going to change their chemical behavior. Changing their chemical behavior means that we have to account for that deviation from ideality with activities. Okay? And what we expect based off of previous discussions is things to get more acidic. And we'll have to just sort of justify that with our answer. So we expect a more acidic solution. As the H plus and AC minus, they can't find each other as much to react back towards the HAC side. Okay, so these I just wrote down for reference. When you're directed to use an activity table and you're given a salt solution, or you're given any solution really, the first step that we kind of realize that we have to do from previous examples is calculate an I sub C. All right, so we have to figure out what the ionic strength of this solution is. Now, we know from our previous examples that the dissociation of HAC, it's not going to really put a substantial amount of ions in solution. It was like 10 to the minus 3. The main thing that's coming in terms of affecting ionic strength, the main thing that's affecting ionic strength, is KCl. So even kind of think about the 10 to the minus 3 that would be added. It would only be affecting this decimal place right here. Really, to good approximation, we can just think about what KCl does in terms of affecting the concentration of ions in solution. We know that this fully dissociates into a K plus and a Cl minus. So our IC is going to be 1/2 of 1 squared, K's charge, times 0.100 molar, right, plus negative 1 squared, which is Cl minus's charge, times 0.100 molar. All right, kind of think about the dissociation, the 1-to-1 ratios. Again, we get a real simple IC that is equal to 0.100 molar. All right, so now I can go on that chart. And the chart that I gave you, the table that has the activity coefficients on there, these are experimental activity coefficients. We kind of trust them a little bit more than our Debye-Huckel theory. Okay, so I go on that chart, and what I find is gamma for H3O plus, which is gamma for H plus, remember those two things are synonymous, looks like 0.83 for that ionic strength. And as always, you'll check my work here. I hope I pulled the right numbers, but again, check and we can correct as we need. All right. Gamma for AC minus, and we kind of have to remember what an acetate looks like, and there's various forms to write acetate as. All right. Gamma for AC minus looks like 0.775. And on the chart, I think they kind of write AC minus as CH3, O2 minus. I think they might write it like that. Okay. But anyway, you're looking for some combinations where you have 2 C's, 3 H's, and an O2. Again, I think they write it like this to kind of show you the structural information and to show you the carboxylic acid group. Okay. But anyway, now, knowing the ionic strength gives me my gammas. So the setup looks a lot like our last example, except we don't have to calculate these gammas. These are our gammas now. We're not going to do an iterative scheme or anything like that. These are the gammas we can use in our calculation. The ICE table is exactly the same. The setup is exactly the same. We're still monitoring HAC and its dissociation. Nothing really changes about our setup except gamma now. So really, we can just piggyback on all that work that we just did, right, in your notes, and we can jump right to our K expression. 1.74 times 10 to the minus 5 looks like my concentration of H3O plus, concentration of AC minus, over concentration of HAC, right, times gamma for H3O plus and gamma for AC minus. Same exact thought process, just different gammas. So we make the same substitutions. 1.74 times 10 to the minus 5 looks like x squared over 0.100 minus x. But now my gamma for H3O plus is 0.83. And my gamma for AC minus is 0.775. We see a nice benefit of using the table gammas. Size of these guys is taken into account, okay? Different ionic atmosphere behavior based off of different actual physical structures of the chemicals involved indicate, right, that we're going to have two different gammas because H3O plus and AC minus, they're going to look different in solution in terms of their chemical behavior. The Bi-Huckel theory assumes that these are the same. Like I said, the main benefit, or one of the main benefits that we have here, besides either experimental, so we trust them more, okay, is that we can get different gammas, okay? So you should be able to solve this for x then, right? And I'm going to leave that work to you. But when you do solve this for x, again, check my work, please. What I get for x is I get 1.64469 times 10 to the minus 3 molar. Now remember, this is my concentration of H plus. This is what I was after. Okay, it looks like we have 3 significant figures there. So I think we get 1.64 times 10 to the minus 3 molar. So relative to pure water, right, in our last Bi-Huckel theory result, what has this done? This has gone up. So remember, this used to be like 1.37 times 10 to the minus 3. So we actually get more H plus in solution. So our idea that, okay, yeah, these K pluses and Cl minuses, they're going to go in here and they're going to keep these H pluses and AC minuses away from each other in terms of reacting back to the reactant side. All those arguments that we made initially when we were looking at activities, it manifests in the mathematics. We see that the result is we get more H plus. Now we did see we still have to check pH. Just because we get more H plus doesn't mean that we have a higher pH, because we know that pH depends on activity. So let's do pH as the negative log of the activity of our H plus, which again is going to look like the negative log of our concentration of H plus and gamma for H plus, right? Well, our concentration of H plus is our X, right? And our gamma of H plus, we know from the previous work that we had written down, is the 0.83. Plug this into this calculation, and what I get for the pH is I get a pH that is equal to 2.8648, and that's all we kind of need. 2.8648, right? Parts hydrogen. Okay. So what happened to the pH? The pH went down. Okay. So now we have to think about why this makes sense, because we just saw an acid example where we didn't have any salt there. There was an extreme amount of ions there. And we saw that the activity really just kind of gave us the same pH in that last example where we had this going into water. So what's the difference here? We do see that there is an activity coefficient that's not 1, right? It's 0.83. So the activity of the ions are affected for sure. But the main difference here is that the concentration went up by a drastic amount, okay? So it used to be 1.3 times 10 to the minus 3, now it's 1.6. So when I say drastic amount, what I mean is this went up enough. Even though we're considering that that concentration doesn't translate to activity, and that those ions in solution that go in solution, they might not be free-flowing, and in fact they aren't, okay? And ion pairing could be occurring, and screening could be occurring of counter ions in ionic atmospheres. This went up by such an amount that the pH went down. Okay. Now it didn't go down a crazy amount, but we do see the effects now of a lot of ions in solution. You can make these solutions more acidic by dumping in a salt, right? If you get enough ions in there, you're going to prevent the actual reformation of the original acid. You'll get enough H+, and even though you're going to get activity coefficients that are going to weaken the effects inside this log, activity coefficients that are going to make this smaller, all right? These will go up by an enough amount, all right, by enough of a value that your pH can still go down. And remember, pH going down means that you're getting more acidic, okay? So there's simply just enough ions in solution to make a more acidic pH. Now this is a nice sort of more streamlined method, and like I said, I actually kind of like it a lot better using a table for gamma. Definitely still need to know how to use the bi-Huckel theory, but we kind of, like I said, trust these gammas more, so this is a real interesting result. Again, we see minor changes. I said the word drastic, and it's really kind of drastic relative to where we were. It's semi-minor changes, but again, if you're doing work where those little differences matter, all right, then you definitely need to consider activities in your calculations. I want to do one last example. Way back in the first video for this week, I promised solubility. And so let's do a problem with solubility. And here again is a situation where when we deal with solubility, we're putting metals in water. And so the concentration of those metals, even if they're trace, knowing the exact concentration, it really matters a lot of the time. So again, if we're going to do it correctly, we need to consider activities and not necessarily concentrations. Okay. So let's just start off with a reminder of what solubility looks like. Let's calculate the solubility of HgCl2 in water. Now I'm going to give you a KSP, but from our last set of videos, all right, one way a professor or a book problem can be tricky is to not give you a K directly for the process that's being analyzed, but to make you go and look up make you go with a delta G naught and give you a temperature and calculate a K. So the only thing I'm going to remind you of here is, remember, for these problems I've been giving you this, but you know how to calculate this based off of previous discussions. So if we do have thermodynamic information about this process instead, there might be some initial work you have to do to get this K. But let's pretend I was nice for this problem and we're asking about solubility and I give you the K straight up. I see that we're going into water. So what we're going to do is we're going to put it in water first using concentrations, using gammas equal to 1. And then we'll analyze the results and decide whether it's dilute enough to just trust the answer that we get or whether we have to consider the ionic strength and go from there. Okay. So for HgCl2, remember what solubility looks like, and we discussed this in lab, right? It looks like a solid breaking down into its ions, and you saw it in general chemistry as well. This is mercury 2. So we're going to get an Hg2 plus, we're going to get 2 Cl minuses, right? So again, back to like environmental implications, mercury is not good to ingest, it does other things to environment, all right? So trace amounts of this actually might be harmful. So we might need an accurate way of getting those trace amounts. Set up our ice table. Q is equal to 0. Q is less than K, right? We're going to move in this direction. We now have a KSP, and we now see that we have E information in our ice table that we can use here. So this is going to be equal to, all right, really it's technically equal to the activity of Hg plus 2, right, times the activity of Cl minus squared, okay? So that's what our K expression really tells us. Our ice table organizes concentration information. So let's take a look at our KSP. For each activity, let's go ahead and let's write down the correct expression, which is activities are concentrations times the appropriate activity coefficient. And now we see the thing with solubility that we have to remember, even from a general chemistry perspective, is that there's sometimes some semi-complicated stoichiometry that you don't find in acid-base chemistry. Everything in acid-base chemistry is 1 to 1 to 1 to 1. We'll kind of get locked into that process. Don't forget that we would need to square this guy. And so then the concentrations would be squared, and so would the gammas. So this looks like 1.4 times 10 to the minus 18. The concentration of Hg plus 2, the concentration of Cl minus squared, gamma of Hg plus 2, gamma for Cl minus squared. Our original K expression had an activity squared, so it's not surprising that for Cl minus we get a gamma squared out in the end. Now, as I mentioned before, what we're going to do to start this problem is we're going to assume that these are equal to 1. So we're going to assume that we have this ideal case, we have a really dilute solution, and we're going to analyze. Okay. So we get 1.4 times 10 to the minus 18. From my ice table, this was X. For my ice table, the concentration of Cl minus was 2X. And I have to remember to square the 2 as well. So what I get here is a simple equation to analyze 1.4 times 10 to the minus 18 is 4x cubed. So when I do this math, I get, with gamma is equal to 1, I get an x that's equal to 7.047298 times 10 to the minus 7. So solubilities are your x's in these problems, so I'll just kind of remind you of that. So whenever you're asked for solubility, it's a molar solubility. It's giving you an idea of the molarity of ions that are put in solution by that insoluble salt, the small amount of ions. This is the concentration of Hg plus 2 in the solution. Notice that it's dilute. So here's how we're going to kind of decide whether we need to include gammas or not, right? If I tell you to, you would analyze from this point. You would have to use the Bi-Huckel theory because on our chart, we don't go down to such small molarities, right? In terms of what gamma could be. And that actually makes sense because remember, we expect gamma to be 1 when we get to really dilute cases, okay? So if you don't see the concentrations on that chart, so if I was going to do an ionic strength of this, it wouldn't be 10 to the minus 7. You would actually have to do the calculation, but it would be small and it would be around there. So until you start hitting those concentrations on your chart, which are like 10 to the minus 3, I think, right? Until you're there, then you can assume that your gammas are equal to 1 and that this is a valid answer, okay? Again, just pay attention to the problem. I could ask you, okay, even though this is dilute, let's use the Bi-Huckel theory and let's crank this out, all right? What you're expected to get, even with the Bi-Huckel theory, is when you actually calculate the I sub c, you expect to get a gamma that's really, really close to 1. Okay, so like I said, we can justify not using gammas that are beyond 1 or deviations from 1 in our gammas, because this is so small. This is actually a good answer. We get about 7.0 times 10 to the minus 7 molar Hg plus 2 in water, right? So maybe that's not toxic, maybe it is, I don't know any of that, but it's a value that we can be confident in. So then what happens to this? All right. When we look at the same solubility, so we're going to be analyzing the same ice table and the same expression, but what we're going to do is we're going to say, okay, well, pure water is really hard to find. There's often other metals, anions dissolved in water as well. So what happens if we're looking at a water sample and we're looking at the solubility of this guy, but it's not a pure water sample, and actually inside that water sample, there's 0.0033 molar calcium nitrate. Okay. So now we say to ourselves, okay, it's not pure water anymore. I know that in pure water I get dilute ions, but okay, I see now that there are other ions floating around that could definitely impact this calculation. So those activity coefficients that I assumed were 1 and then justified as being 1 for my answer, because all my answers were so dilute, I can't use those same justifications now. So what we're going to do is we're going to have to calculate I sub c. And then for this problem, what we're going to do is we're going to use a table to actually do this calculation. Okay. And I would direct you in that way. So this is our first non-simple I sub c calculation. All right. And why I say that is you kind of have to think about what happens. This is 0.0033 molar calcium nitrate. Calcium nitrate breaks down into Ca plus 2 and 2 NO3 minuses. So now why is that important? Remember when we do our IC, okay? We already know that these ions aren't going to influence this drastically. So we really can just focus in on the ions here. So it's going to be 1/2, all right, the charge of calcium, right, calcium plus 2, squared, times the concentration of calcium plus 2, right, plus the charge of NO3 minus squared, and the concentration of NO3 minus in our solution. So there's more complications here than the other I sub c's that we've been looking at, okay? I sub c, right, is 1/2. The charge of calcium is 2. 2 squared is 4, right? Calcium plus 2, here's the molarity of my salt. Calcium has a 1-to-1 relationship with that molarity. So the molarity of my calcium is going to be 0.0033 molar. The charge of my nitrate is 1. If I square 1, sorry, it's -1, but if I square -1, I get 1. There is a 2-to-1 ratio, right, between the concentration of your salt and how much nitrate gets thrown into that solution. And remember, this is a completely soluble compound. It's not going to have a KSP or anything like that. You can assume it completely dissociates. This 2-to-1 ratio dictates that my concentration of NO3 minus, it's not 0.0033. I get 2 NO3 minuses for every Ca plus 2. I get 2 NO3 minuses for every time the salt dissolves, I get 2 NO3 minuses. So this concentration is 0.0066 molar, okay? It's twice, right, the molarity of the salt. So you do have to pay attention to stoichiometric coefficients. You do have to pay attention to charge, right, when you're doing these I sub c calculations. So when I do this math, what I get for I sub c is I get 0.0099 molar. Now this isn't exactly on your chart, so when I dictate that you use something on your chart, you find the column that matches best. On your chart, you do see, right, a column that looks like 0.010 molar, right? So these values are close enough that I'm going to be able to look and say, okay, my I sub c to a good approximation is this. So those gammas for Hg plus 2 and Cl minus with this concentration are going to be valid, okay? So whenever you calculate an I sub c, you just find the closest value on that chart to then pick out what your gammas are, right? When I do that, and I know I keep saying it, but like I keep mentioning, everything's new, so please check my work so we can make corrections as needed. When I look on that chart, if I read it correctly, what I get is gamma for Hg plus 2 at that ionic strength that we just justified is 0.67. And I get a gamma for Cl minus that looks like 0.899. Okay. Now remember, nothing about our setup changes, nothing about our ice table changes, but are these gammas now 1? No. So we expect to get drastically different answers because of the presence of these ions in solution, okay? And that makes sense from the solubility standpoint. There's going to be prevention of the ions coming back together to make the solid. And we'll kind of justify that at the end. I'll go over all that one more time. So our expression looked like 1.4 times 10 to the minus 18 was equal to, right, concentration of Hg plus 2, concentration of Cl minus squared, Activity coefficient for Hg plus 2, activity coefficient for Cl minus squared. Nothing really changes about that analysis at all, okay? Except, again, we're going to put in these values in the correct spot. So what we get is a slightly different mathematical equation to solve, so we're going to get a slightly different x. So we get 1.4 times 10 to the minus 18, right? Looks like, when I do this math, I get 4x cubed again, but all this other gamma stuff is going to give me 0.591495. Okay. I can now solve for x. This is a multiplicative factor, divide over. Oh, it looks like I'm definitely going to get a different x. And when I solve for that x, it looks like we get 8.646 times 10 to the minus 7 molar. That is the solubility under these conditions. The solubility went up by 8-fold. Just because we were considering, oh, the sample of water might have other ions in it like calcium nitrate. Okay? So it went up by a factor of 8. Again, the Gen Chem answer would be no effect. But our answer now is, oh yeah, the ionic atmosphere is changing. The activities are changing. You actually get more ions in solution. A higher concentration. Remember, that's how you view these solubilities from general chemistry. You view them as how many ions go into solution, or molar concentrations of ions. So one last time, let's make sense of our answer. We have a solid breaking down into aqueous components. But this process, okay, is a two-way street. This process is in equilibrium. So HgCl2s are breaking down, right? And Hg plus 2s and Cl minuses are coming back the other way. So why did our solubility go up when now we have calcium nitrate in solution? There's also big plus 2s floating around. There's also big minuses floating around. In fact, there's 2 of them. Are these guys going to get in the way of this process? Are these guys going to affect these ionic atmospheres to the point where we really can't say it's just a free-floating Hg plus 2 and a free-floating Cl minus, purely dilute and far away from each other? These guys definitely have an impact on what these guys do in solution. The plus 2, right, could repel these guys, keeping them away from your Cl minuses, right? These guys have to get near each other. Well, there could be other ions in the way, either attracting or repelling, okay? Oh yeah, these are nitrates, not Cl minuses, sorry. These inert ions, the Ca plus 2s and the nitrates, right? They get in the way of the reverse process. Getting in the way of the reverse process dictates that this forward process becomes more favored relative to the pure water case. So what do we see? We see a higher solubility. More of this would dissolve, right? More would dissolve because of this interference effect of these ions, right? So I know we justify the physical explanations a lot, but that's an important part for these sorts of problems. You now see how to do these problems, and we've done a series of examples together. Your homework is focused in on, okay, you did a whole week of Gen Chem level equilibrium. Now we're going to step it up, and we're going to do equilibrium problems with this sort of approach where we have a gamma that we can get from a table or a gamma we can get from Debye-Huckel theory, and then we analyze our answer in terms of activities of ions being affected by the presence of other ions in solution.